Welcome to The Deep Dive, the show where we journey into the complex digital landscape and emerge with clear, actionable insights. Think about your day for a second. How many apps do you tap, swipe, or click through? Your streaming service, maybe that banking app, your smart thermostat, even the map on your phone, it's probably dozens, right? Maybe even hundreds, if you count everything. And have you ever paused to wonder what invisible digital force is orchestrating all that seamless connectivity? That constant flow of information between, your device and just a myriad of online services. What's that? Like digital magic under the hood.
It's a really insightful question, actually, because what often feels like magic is, well, it's incredibly sophisticated engineering at work, elegant almost behind the scenes. Today, we're pulling back the curtain on one of the most vital, yet often unsung heroes in that huge digital infrastructure,
Yeah,
the API gateway.
that's it. The API gateway. We're shining a spotlight on the digital traffic cop, the unsung hero, the absolute cornerstone of modern digital architecture. It's the quiet orchestrator that allows everything from your favorite video game to your critical healthcare app to securely talk to hundreds, maybe even thousands of back-end systems. And you never even have to notice the dizzying complexity involved. For this deep dive, our mission is pretty clear. We're going to unpack exactly what API gateways are, explore why they've become just utterly indispensable in our microservices and cloud-native world, dissect how they deliver significant, tangible business value, and finally, we'll peer into the exciting trends shaping their future. By the end of this conversation, our goal is for you to walk away not just informed, but with a really comprehensive, almost intuitive grasp of this critical technology. So let's dive in.
Absolutely. And, to truly grasp the what and the how of API gateways, we first need to understand the fundamental why.
Mm-hmm.
Why did these powerful components become so essential in the first place? It's really a story of architectural evolution, a journey from, well, relative simplicity to an explosion of complexity,
Mm-hmm.
which then demanded an entirely new kind of solution to bring order to the chaos.
All right, let's trace that journey. So, for a very long time, software applications were built like these giant, self-contained medieval castles, I guess you could say. We called them monoliths.
Yeah.
Every single function, user management, product catalog, payment processing, it was all bundled into one massive, indivisible unit.
One big block.
Exactly. And if you wanted to change even a small window on that castle, say just update the login process, you often had to re-architect or, rebuild a large part of the entire structure. It was slow, cumbersome, incredibly risky to deploy. And scaling. Scaling became a nightmare. One small bug could bring the whole castle crashing down.
Precisely. Then came an attempt to break these monolithic giants into more manageable pieces. That led us to service-oriented architecture, or SOA. This approach aimed to encapsulate functionalities into distinct, reusable services. Which sounds good, right? But often SOA introduced its own set of complexities. It could feel a bit like a convoy of heavily armored, slow-moving vehicles, often relying on heavyweight technologies like enterprise service buses or ESBs.
ESBs, right. I remember those, like a central hub for everything.
Yeah, think of an ESB as a central nervous system for all your applications, translating messages between them. And while it offered some modularity, it could also become a single, complex bottleneck itself. It required significant overhead to manage. The real paradigm shift, the truly agile and scalable approach, came with the microservices revolution.
Ah, the microservices revolution. This is where pioneering companies like Netflix and Amazon really, really showed what was possible. Instead of one giant application, they broke everything down into hundreds, sometimes thousands, of tiny independent services, each one designed to do one thing exceptionally well. Imagine our medieval castle transforming into this bustling, vibrant, modern city. Each microservice is like a highly specialized business, or Shop One handles user profiles, another processes orders, a third manages product recommendations. They all operate independently, can be updated or scaled without affecting the others. But here's where the challenge emerged, or rather, the problem.
Right, the coordination issue.
Exactly. How do you manage all these thousands of independent services talking to each other and to various client applications like your phone, web browser, or even a smart TV? It's like having thousands of businesses in our city, and every single one needs to be discoverable, reachable, and secure.
That's the crux of it. That incredible decentralization of functionality created a massive management headache. Suddenly, you had what we refer to as cross-cutting concerns.
Oh.
These are vital aspects like authentication, proving who you are, or authorization, what you're actually allowed to do, or rate limiting, preventing any single user or system from just flooding your services with too many requests, or even just monitoring performance across such a distributed landscape. It gets complicated fast.
Yeah, things everyone needs, basically.
Exactly. These crucial functionalities are needed across all those hundreds or thousands of microservices. Now, if you try to embed them into each individual microservice, well, you're looking at immense inefficiency, duplicated code, and a consistent nightmare for managing consistency, updates, error handling. It's just a recipe for operational chaos.
So, extending our city analogy, if you're building this bustling metropolis of microservices, you absolutely cannot have every single business building its own front gate, right? Its own security checkpoint, its own welcome desk, its own unique set of rules for visitors. It would just be an unmanageable mess.
Totally unmanageable.
That fragmentation immediately highlighted the critical need for a centralized control point, a single intelligent entry point to manage all that incoming API traffic where all those cross-cutting concerns could be handled uniformly. And that, in a nutshell, led directly to the birth and, well, the spectacular rise of the API gateway. It became the central nervous system for managing external interactions with your distributed applications.
Indeed. And its relevance has only intensified over time. In today's hyper-connected digital world, an API gateway isn't just, a convenience. It's truly mission-critical infrastructure. We've largely moved into an API-first development paradigm.
API first, right. That's a big buzzword.
It is, but for good reason. APIs are no longer an afterthought or some technical detail buried deep within the application. They are explicitly viewed as primary products, essential for competitive advantage, for opening up new business models. Consider how many services you use daily that rely on robust external APIs, payment processors, mapping services, social media integrations, even the weather app on your phone. Their reliability often hinges on API gateways doing their job correctly.
And then, the past few years just turbocharged this whole evolution, didn't they? The sudden and sweeping digital transformation, accelerated by the COVID-19 pandemic, forced businesses to pivot almost overnight to online-first models.
Absolutely. It was a massive shift.
They had to scale rapidly, dealing with unprecedented traffic spikes, entirely new integration requirements. Robust, scalable, and secure API infrastructure became absolutely crucial. A survival imperative, really, to support these sudden shifts without compromising security or performance. For many, the API gateway was the very technology that allowed them to survive and, frankly, thrive through that period of intense change.
Absolutely. And beyond that immediate acceleration, just consider the sheer proliferation of devices connecting to the Internet. The Internet of Things IoT now encompasses billions of connected devices, everything from smart home gadgets to industrial sensors, and the continuous explosive growth of mobile applications, which are often just a beautiful user interface on top of a complex web of APIs.
Right, the app is just the tip of the iceberg.
Exactly. This further amplifies the need for efficient, secure, and manageable API traffic. Each of these devices and apps represents a potential connection point that needs to be handled intelligently, securely, and at scale.
It's not just about performance and scalability, though, is it? Regulatory compliance plays an absolutely huge and maybe often underestimated role here. We're talking about global regulations like GDPR for data privacy, iPay for healthcare data protection in the US, or PCI DSS for payment card security.
Very strict rules.
Incredibly strict requirements for handling sensitive data. An API gateway is critical because it provides that centralized, enforceable point for policy enforcement and audit capabilities. You can program rules directly into the gateway that ensure every request coming into your system adheres to these stringent regulations. It makes compliance far more manageable and verifiable than trying to implement it in every single back-end service. That sounds impossible.
It's practically impossible to do consistently otherwise, and the market certainly reflects this criticality, doesn't it? We're seeing truly explosive growth in this space.
Okay.
It indicates a widespread recognition of their value.
Explosive is genuinely an understatement. Our sources paint a staggering picture. The API gateway market alone is projected to reach an incredible $15.6 billion by 2033. Yeah, that's up from just $3.6 billion in 2023. That represents a compound annual growth rate, or CAGR, of 15.6%. That's a huge expansion in just a decade.
And if you zoom out to the broader API management market, which includes not just the gateway, but the entire lifecycle management of APIs, from design to monitoring, the numbers are even more dramatic. It's expected to reach $32.48 billion by 2032, leaping from $6.85 billion in 2025. Another source even projects the global API management market could reach an astonishing $51.11 billion by 2033, from $6.63 billion in 2024. That's a robust 24.20% CAGR.
50 billion.
50 billion.
That.
And it's interesting, North America currently dominates the market share, over 38.9%. But Asia-Pacific is showing the highest growth rate, primarily driven by massive IT infrastructure investment and accelerated cloud adoption in that region.
Those are truly phenomenal numbers. And if we connect them back to the bigger picture, it clearly shows this immense growth isn't just a fleeting trend. It comes directly back to the driving forces we just discussed. The ubiquitous microservices revolution, the widespread proliferation of cloud computing, the increasing and often business-critical usage of APIs across every conceivable industry, and the fundamental adoption of API-first strategies by leading organizations. It's not just a technical component anymore. It's a fundamental shift in how digital business is conceived, built, and executed. The market isn't just growing, it's recognizing a foundational necessity. So we firmly established why API gateways became so important. Now let's peel back another layer and get into the what. What exactly is an API gateway, beyond just our helpful digital traffic cop metaphor?
Right. At its core, an API gateway is a sophisticated architectural component that acts as the single entry point for managing, routing, and securing all API traffic. All the traffic flowing between client applications and your vast array of back-end services. Think of it as the ultimate concierge for all your digital interactions. When a client application wants to talk to your services, it doesn't try to find individual back-end servers. It goes straight to the gateway.
So it's not just passively passing traffic straight through then. It sounds like it's doing a lot more than just opening a door.
You're exactly right. It's far from passive. It fundamentally functions as a reverse proxy, sitting strategically in front of your microservices. This provides a unified, consolidated interface that completely abstracts away the internal complexity of your underlying, often numerous and dynamically changing, back-end services. For example, your mobile app doesn't need to know that your user profile service is at one IP address and your order processing service is at another. It just talks to the gateway, and the gateway handles the sophisticated routing and redirection. This simplification for the client is a massive advantage.
Okay, that analogy of a unified concierge makes perfect sense, like having one main reception desk for a sprawling multi-department company, and the concierge directs your call or visit to the right department without you needing to know the internal floor plan. So what are its essential sort of must-have functionalities?
Its core functionalities are quite extensive and powerful. First, there's request routing, which intelligently directs incoming requests to the appropriate back-end services based on predefined rules. Path-based routing, header-based, etc. For instance, a request for users might go to the user service, while orders goes to the order service. Simple example. Then protocol translation, which is crucial for modern, diverse architectures.
So handling different languages, essentially.
Yeah, kind of, yeah. It can seamlessly convert between different API protocols. Perhaps your external clients use traditional REST, but your internal microservices communicate using newer, faster protocols like gRPC or flexible query languages like GraphQL. The gateway handles that translation on the fly, smooths everything out. It can also perform traffic composition. This is a really powerful feature where the gateway aggregates data and responses from multiple back-end services into a single, unified response for the client.
Oh, interesting. Like combining results.
Exactly. Imagine displaying a user's dashboard that needs data from their profile, their order history, and maybe their notification services. The gateway can fetch all that, combine it, and send it back as one cohesive response. Much more efficient for the client. And critically, it performs policy enforcement, implementing vital rules for security, rate limiting, compliance, right at the edge before requests even reach your core services.
That's impressive, and I've heard they've evolved quite a bit, offering much more than just the basics now.
Oh, absolutely. Modern API gateways are powerhouses packed with advanced capabilities. They include robust caching, which stores frequently accessed data and speeds up responses by serving them directly from the gateway without needing to hit back-end services every time.
Saves a trip.
Exactly. There's also intelligent load balancing, which distributes incoming traffic efficiently across multiple instances of your back-end services to prevent any single one from being overwhelmed. Keeps things stable. They also implement circuit breaker patterns. This is a crucial resilience mechanism that prevents cascading failures in distributed systems.
Circuit breaker, like in my house.
Sort of. If a back-end service starts struggling or becomes unresponsive, the circuit breaker trips, temporarily stopping requests to that specific service. gives it a chance to recover, and crucially, prevents your entire system from grinding to a halt because one part failed. And finally, they offer robust observability features for comprehensive monitoring, logging, and troubleshooting, giving you deep insights into your API traffic. You need to see what's going on.
What's truly fascinating here, beyond just the features themselves, is the underlying blueprint for reliability and scalability they're built on. What are the fundamental architectural principles at play that allow API gateways to handle such immense scale and complexity?
Yeah, the design is key. A cornerstone principle, as we've already touched upon, is that single point of entry. It might seem counterintuitive, right? Introducing a potential bottleneck.
Yeah, that's what I was thinking.
But it fundamentally simplifies client implementations and, crucially, centralizes control. Imagine trying to manage authentication, authorization, or security policies if every client could talk to any of your hundreds of back-end services directly. It would be an unmanageable, unsecured nightmare. The gateway ensures all external traffic flows through one controlled, secure, and observable choke point.
That sounds like an absolute nightmare to maintain, trying to do it individually.
It undeniably would be. Another crucial principle is the separation of concerns. This divides the API gateway's functionality into two distinct, independently manageable parts: the control plane and the data plane. This separation is absolutely key to their scalability and resilience.
Okay, let's unpack those. What's the fundamental difference between the control plane and the data plane? It sounds a bit abstract.
Let's use our city analogy again.
Yeah.
The control plane is like the city planning department and its regulatory bodies. This is the administrative side, where you, as an architect or administrator, define all your policies, configure your routing rules, manage security settings, update your gateway's behavior. It includes components like a management API for programmatic configuration, allowing automation tools to update rules, which is huge for DevOps, a policy engine to interpret and compile your high-level rules into executable logic, and a configuration store, often using highly distributed, consistent databases like etc. or Console to maintain a synchronized state across all your gateway instances. This is where you tell the gateway what to do and how to behave.
So the control plane is like the brain, basically, setting the rules and strategy. What about the brawn, the actual execution?
Exactly. The data plane is the city's bustling traffic management system, the actual roads, traffic lights, intersections, along with all the individual vehicles flowing through. This is where the real-time processing happens. When an API request comes in, the data plane handles it. It includes a request router that intelligently directs the request to the correct backend service based on the rules from the control plane. The load balancer that distributes that traffic evenly across multiple instances of that service to ensure no single one is overwhelmed. And the protocol adapter that handles any necessary transformations between client and backend protocols. This is where the actual work gets done, enforcing the policies that were defined up in the control plane.
That makes the separation much clearer. So why split them? What's the big practical advantage of having these two distinct parts?
The separation allows for independent scaling and superior fault isolation. Think about it. You can scale your data plane instances horizontally, adding more traffic controllers and roads, essentially based on your live traffic demands. And you can do that without affecting your administrative functions or needing to reconfigure everything. If one data plane instance fails, others can pick up the slack seamlessly without impacting the control plane or the overall system's availability. It offers profound operational flexibility, resilience, and allows for continuous delivery of updates to your gateway configuration without downtime.
That sounds incredibly robust. What other principles are vital to their design?
Stateless design is another critical principle, specifically for the data plane. This means that individual gateway instances don't store any session-specific information about a particular user or request between interactions. Each request contains all the information needed for the gateway to process it.
No memory of past requests.
Essentially, yes. This is immensely powerful because it enables elastic scaling. You can add or remove gateway instances dynamically without worrying about losing ongoing user sessions. It also vastly simplifies load balancing, as any instance can handle any request, and significantly improves fault tolerance, as the failure of one instance doesn't disrupt others. If any state information is needed, maybe for session tokens or rate limit counters, it's externalized. It's pushed out to highly available shared storage systems like Redis.
And given how many different ways applications can communicate today, I imagine protocol agnosticism is huge, being able to speak multiple languages.
It absolutely is. A modern API gateway's ability to handle multiple communication protocols, the widely used HTTP, HTTPS, WebSockets for real-time, persistent connections, gRPC for high-performance microservices communication, and increasingly GraphQL for flexible data access is crucial. This provides immense flexibility for integrating diverse ecosystems and back-end services. It allows you to choose the best protocol for each specific use case without forcing all clients or services into a single rigid standard.
That's a really deep dive into the what. Now let's zoom in even further on those inner workings. Can you detail the actual architectural components within the control and data planes and those cross-cutting services that sort of tie everything together?
Certainly. Let's start with the control plane components. As mentioned, you have the management API. This is a programmable interface that allows for automated configuration of your gateway, vital for modern DevOps practices, enabling seamless integration with CI/CD pipelines so you can manage your gateway's rules and policies just like any other code. Infrastructure as code.
Nice. Makes it repeatable.
Exactly. Then there's the policy engine. It takes your high-level, human-readable rules, like only authenticated users can access this API, or limit this customer to 100 requests per minute, and translates them into executable logic that the data plane can understand and enforce. And finally, the configuration store using distributed systems like Etc. or Console ensures that all your gateway instances operate with the exact same consistent rules and settings. Maintain perfect synchronization across your entire fleet.
Okay. And on the real-time processing side, our traffic management system, the data plane.
For the data plane, the request router is the first point of contact after the request hits the gateway. It analyzes the incoming request, its URL path, headers, HTTP method, maybe other things, and intelligently directs it to the correct backend service. The load balancer then steps in to distribute that traffic evenly across all available instances of that chosen backend service, prevents overload, maximizes efficiency. And the protocol adapter is the unsung hero that ensures smooth communication. It takes a request in one protocol, say REST from a mobile app, and translates it to another, like gRPC for an internal microservice, and then translates the response back again for the client. Seamless.
Beyond those core routing and processing engines, what about those essential services that cut across everything, ensuring security and stability? You mentioned those earlier.
Those are absolutely critical and often define the true value of an API gateway. Authentication and authorization are paramount. The gateway acts as the first line of defense. That leverages industry standards like Oath 2.0 and OpenID Connect to securely verify user identities and determine what actions they are permitted to perform. Critically, modern gateways often rely on JSON Web Tokens, or JWTs, for stateless authentication.
JWTs, right. Those are like digital passports.
That's a great analogy. A JWT is like a tamper-proof digital ID card that contains all the necessary user information, digitally signed. The gateway can validate this token locally without needing to constantly query a central identity server. This significantly boosts scalability and performance. Less chatter.
And to prevent system abuse and ensure fair usage for everyone, making sure no one hogs all the resources.
That's where rate limiting and throttling come in. These mechanisms control the number of requests a client, or maybe an API key, can make within a given time period. This prevents malicious actors from launching denial of service attacks by just flooding your system. And it also ensures that a single hungry client doesn't consume all your resources, guaranteeing fair access for all users. And finally, a powerful caching layer dramatically improves performance by storing frequently requested data directly within the gateway. When a subsequent request comes in for the same data, the gateway can serve it instantly from its cache without needing to hit the backend service, drastically reducing latency and load on your services.
And to make sure everything is running smoothly, we need deep visibility, right? You can't fix what you can't see.
Exactly. Observability components are essential for any complex distributed system. This isn't optional anymore. This includes comprehensive metrics collection to gather real-time performance data like latency, throughput, error rates, giving you a pulse on your system's health. A robust logging subsystem captures detailed information about every request and response, invaluable for debugging and security auditing, and crucial for microservices, distributed tracing integration. This allows you to follow the entire journey of a single request as it flows through multiple services in your distributed system. This end-to-end visibility is absolutely invaluable for pinpointing performance bottlenecks or troubleshooting errors in a complex environment. You can see exactly where things slowed down or failed.
That's an incredibly comprehensive look at the what. Now let's turn to the how. How do organizations actually implement these powerful API gateways in practice? And what kind of benchmarks define a fast and reliable gateway? What should people be aiming for?
Right, the practical side. The deployment approach for an API gateway depends heavily on an organization's existing architecture, specific needs, and, importantly, future scalability goals. One of the most common and straightforward patterns is the centralized edge gateway. Here, A single cluster of API gateways is deployed right at the network edge, managing all external API traffic coming into the organization. It offers simplified management and centralized policy enforcement, provides a clear security boundary for all inbound requests. Pretty standard starting point.
But I imagine centralizing everything comes with its own set of trade-offs, doesn't it? Like a single point of failure if not handled correctly. Or a bottleneck.
It certainly can. If not designed for extreme high availability and sufficient capacity, a centralized gateway can indeed become a bottleneck, or, as you said, a single point of failure for your entire system. You have to build in redundancy. To mitigate this and address growing scale, some organizations opt for a two-tier gateway architecture. This separates the external gateway layer, which primarily focuses on public-facing concerns like security, rate limiting, protocol translation, from internal gateway layers that manage communication between microservices.
Ah, so like an outer wall and an inner gate.
Kind of, yeah. The internal layer prioritizes performance, service discovery, and perhaps finer-grained internal policies. This separation allows for immense scalability and targeted optimization for different types of traffic, external versus internal.
That tiered approach makes a lot of sense for larger, more complex environments. What about getting the gateway closer to the services themselves, reducing that network hop? I hear about that a lot.
That's where micro-gateway deployments come into play. These are lightweight gateway instances co-located with specific services or small groups of related services. The main advantages here are significantly reduced latency because the gateway is physically closer to the service it's protecting.
Less travel time.
Exactly. And improved fault isolation. A problem with one micro-gateway doesn't necessarily affect other unrelated services. It's ideal for very high-performance, low-latency scenarios.
So less latency, better isolation. But I can imagine it adds complexity, managing lots of little gateways.
You're spot on. The trade-off is increased operational complexity. Managing many lightweight distributed instances can lead to configuration drift if not handled meticulously. You need robust automation and configuration management tools to keep everything consistent. Another related and increasingly popular approach is sidecar proxy integration. This aligns closely with service mesh architectures like Istio or Linkerd.
Service mesh, right? We'll touch on that later.
Yeah. Here, gateway capabilities are embedded directly into the service mesh's data plane, often as a proxy container running right alongside each microservice, like a little helper attached to each service. This offers seamless integration with internal microservices traffic management, providing unified observability and policy enforcement across both internal and external communication. Blurs the lines a bit.
And with the rise of IoT and real-time applications, I'd guess edge computing is playing a significant role here too, bringing the compute closer to the data source, closer to the user.
Absolutely, it's a critical frontier. Edge computing integration involves deploying lightweight gateways closer to the actual users or data sources, literally at the edge of the network. Think smart factories, remote IoT sensors, or content delivery networks. This provides ultra-low latency responses, which is crucial for real-time applications like augmented reality or autonomous systems. And it optimizes bandwidth by processing data locally before sending only relevant information back to central data centers. It's about decentralizing the intelligence.
Beyond deployment models, what are the key features and integrations that truly make these gateways the powerhouses they are for managing APIs? What enables them to unlock so much value?
Well, at their very heart, the robust authentication and authorization capabilities are foundational. They support widely adopted industry standards like Oath 2.0 and OpenID Connect for secure identity management. Oath 2.0, for instance, allows a user to grant a third-party application limited access to their data without sharing their password. It acts as a secure digital key dispenser.
Like login with Google.
Exactly like that. OpenID Connect builds on this by adding identity verification. As we mentioned, JSON Web Tokens, or GWTs, are often preferred for stateless authentication. These cryptographically signed tokens allow the gateway to validate a user's identity and permissions with high performance. All the necessary info is contained within the token itself, avoiding constant database lookups.
And I know GraphQL is a massive paradigm shift for many developers, very different from traditional REST. How do gateways handle that flexible query approach?
GraphQL integration is indeed increasingly important for modern applications. It allows clients to request exactly the data they need and nothing more from potentially multiple sources, all in a single query.
Very efficient.
Very. Modern gateways offer specialized features for GraphQL, including things like query parsing, schema validation against your backend schema, and caching optimization specifically for GraphQL queries. This flexibility allows clients to consume APIs more efficiently and reduces overfetching of data, which is a common problem with traditional REST APIs, where you might get way more info than you needed. It's like being able to order exactly what you want from a restaurant menu rather than getting a fixed course meal you can't change.
And to prevent system abuse and ensure fair usage across all consumers, we talked about rate limiting.
That's precisely where rate limiting and throttling become indispensable. These sophisticated mechanisms control the number of requests a specific client, an IP address, or maybe an API key can make within a defined time period, say 100 requests per minute. This prevents malicious actors from launching denial of service attacks by just overwhelming your services with traffic. And it also ensures that no single legitimate user monopolizes your resources, guaranteeing consistent availability and performance for everyone. And finally, monitoring and logging. Absolutely essential. They provide the critical telemetry needed for performance tracking, real-time error detection, and security auditing. Comprehensive logs and metrics allow operations teams to quickly identify issues, troubleshoot problems, and ensure continuous system health and security. Without this, you're just flying blind.
This all sounds fantastic in theory, but how do we know if an API gateway is actually performing well in the real world? What are the key performance metrics that organizations rigorously track to gauge their effectiveness? What are the numbers people look for?
Right, the benchmarks. The single most critical indicator is latency. This measures the total time it takes for a request to be processed end-to-end, from the moment it hits the gateway to when the response is returned to the client. Lower is better, obviously. Industry leaders deploying highly optimized gateways are achieving truly impressive numbers. We're talking P99 latency of just 2.3 milliseconds.
P99. Okay, for our listeners, that's a very specific term. Can you explain what P99 latency means and why it's so important compared to just an average latency number?
Absolutely. P99 latency means that 99% of all requests are completed within that stated time. So 2.3 milliseconds in this benchmark case. Only 1% take longer. It's a far more robust and realistic metric than just average latency, because the average can hide a lot of painful outliers.
Right, a few really slow requests can skew the average badly or get hidden.
Exactly. If your average latency is low, but your P99 is high, it means 1% of your users are having a terrible experience, potentially waiting seconds or even tens of seconds for a response. P99 focuses on the tail end of your performance distribution, which is often where user frustration, churn, and ultimately lost business truly lie. It directly speaks to the quality of experience for the vast majority of your users, especially under heavier or peak loads. It's a much better measure of consistency.
That's a powerful distinction. Focus on the experience, not just the average. And what about the sheer volume of requests these gateways can handle? How do we measure that capability?
That's throughput, typically measured in queries per second, or QPS. Sometimes transactions per second, TPS. This metric tells you how many API requests the gateway can successfully process in a given second. Higher is better here. High-performance implementations can achieve an astounding 160,000 QPS.
Wow, 160,000 requests every second.
Per second. To put that into perspective, that's enough capacity to handle the intense traffic spikes during something like a Black Friday sale for a major e-commerce platform, ensuring every customer's transaction goes through smoothly without frustrating server-busy errors.
And what about the resources they consume to achieve these incredible speeds and volumes? We don't want them to be resource hogs, right? Taking up all the server power.
Not at all. Resource utilization is a key optimization target. Optimized gateways are designed to be incredibly efficient, consuming minimal CPU and memory. For example, depending on the configuration, features enabled like caching and the volume of traffic, they might use anywhere from maybe 100 millib to several gigabytes of memory. Lean is good. A healthy, well-configured deployment typically maintains an error rate below 1%. This indicates high reliability and stability under normal operational conditions. And for enterprise-grade deployments, the target for availability is often a remarkable 99.99%, sometimes even higher.
4 nines. It's not much downtime at all.
It translates to less than an hour of downtime per year, maybe even just minutes. This is achieved through robust redundancy, automated failover mechanisms, and active setups across multiple data centers or cloud regions. You need that for mission-critical systems.
So with these impressive benchmarks in mind, who are the major players in this space? Which tools and technologies are organizations actually using to achieve these kinds of numbers?
It's a robust and highly competitive market,
Yeah.
definitely. Among the undisputed market leaders, we have Kong Gateway. Kong is often cited for its exceptional performance, capable of handling over 50,000 transactions per second TPS per node. That's huge. It boasts an incredible footprint with 345,000 publicly exposed instances and is utilized by over 37,000 companies worldwide. Massive adoption.
Okay, Kong's a big one.
Then there's Google Apogee. It's known for its comprehensive enterprise features, AI-driven analytics, and powerful monetization capabilities, often used by large enterprises. And of course, the major cloud providers offer their own robust, fully managed services. Amazon API Gateway and Azure API Management. Both provide seamless integration with their respective cloud ecosystems, simplifying deployment and scaling for cloud-native applications. Very popular choices if you're already in AWS or Azure.
And for those who prefer more control, perhaps open source solutions, or have specific performance needs beyond the big cloud providers.
The open source solutions are also incredibly strong and innovative. Apache API X, for example, is a high-performance cloud-native option built on NGINX and LuaG. It boasts 147,000 deployments and is used by over 5,200 companies. It's celebrated for its dynamic features, extensibility, and performance.
Apache API X, okay.
NGINX Plus leverages its proven reverse proxy technology.
Dang.
NGINX is everywhere to offer advanced API management capabilities, particularly popular for those already familiar with NGINX. And Trifix specializes in cloud-native deployments with automatic service discovery, making it ideal for containerized environments like Kubernetes. Very slick integration there. For enterprise commercial solutions, beyond the big ones, you have Tyke. It's known for its developer-friendly interface and comprehensive API management lifecycle features. And KrakenD, which specifically focuses on ultra-high-performance microservices integration. It's often preferred in Europe, used by 2,000 companies specifically for its speed and efficiency in stitching services together. It's truly a diverse and innovative space. There's a solution out there for nearly every need, every scale, every budget.
So we've dissected the why, the what, and the how. Now let's move to the tangible real-world impact. Where are API gateways truly mission-critical today, and what specific concrete problems are they solving in these diverse sectors?
Right, where the rubber meets the road. API gateways are no longer optional. They're indispensable across an incredibly vast array of industries. They're the digital backbone. Take financial services, for instance. Here, security, compliance, real-time performance. These are not just priorities, they are absolutely non-negotiable.
Table stakes.
Totally. API gateways are the enablers of open banking initiatives, securely managing the exposure of financial data to trusted third-party applications. They facilitate real-time payment processing, ensure strict regulatory compliance with standards like PCI DSS for credit card data and GDPR for customer data privacy. They provide the ironclad security and seamless customer experiences that we now just expect from our mobile banking apps and online payment platforms.
That makes perfect sense for banking, given the sensitive nature of the data. What about something like healthcare, where data privacy is equally, if not more, paramount, Usmampia and all that?
In healthcare, API gateways are equally vital, maybe even more so, for hypercompliance and robust patient data protection. They enable secure and auditable data sharing between disparate health systems, think hospitals, clinics, labs. They support the rapid growth of telemedicine applications, allowing virtual consultations securely. And they facilitate the integration of an explosion of IoT medical devices, like continuous glucose monitors or smart inhalers, sending data back safely. The gateway ensures critical audit trails are captured, robust access controls are enforced, and sensitive data is encrypted. Paramount in such a highly regulated and sensitive sector where data breaches can have just devastating consequences.
And in the world of entertainment, where massive traffic and instant access are the norm, especially for streaming services like Netflix or Disney+.
Media and entertainment companies rely heavily on API gateways to handle their immense scale. For those big streaming services, API gateways manage pretty much everything, from content delivery, making sure the video gets to you, to user authentication, personalizing recommendations, and crucially, handling massive, concurrent user loads. Think of millions of people all trying to stream a new show the moment it drops.
Yeah, the load must be incredible.
It is. They enable global content distribution, enforce regional content restrictions based on licensing agreements, and ensure personalized viewing experiences, all while upholding content security and guaranteeing optimal performance, preventing buffering or glitches during peak demand. The gateway is central to that smooth experience.
Finally, what about the industrial world? Manufacturing and the explosion of IoT devices there, connecting everything from factory floors to supply chains.
In manufacturing and IoT, the focus for API gateways shifts dramatically towards edge computing integration, device management, and real-time data processing. Gateways connect myriad factory equipment sensors, machines, robots. They manage complex supply chain integrations between different companies. And they enable cutting-edge applications like predictive maintenance for industrial machinery, anticipating failures before they happen based on sensor data.
Saving downtime.
Exactly. They provide crucial protocol translation, allowing legacy industrial equipment, which often speaks older languages, to communicate with modern cloud systems. They perform data aggregation at the edge, enforce robust security for industrial IoT environments, often right there on the factory floor, ensuring minimal latency and high resilience for critical operations.
It's clear they're widely adopted and foundational, but let's talk about some concrete success stories. The proof, as they say, is in the pudding. Can you share some compelling examples of organizations that have truly transformed their operations or achieved remarkable results by leveraging API gateways?
Absolutely. One compelling example comes from Honor, the global smartphone manufacturer. They achieved remarkable results using Apache APISX, leveraging its high-performance capabilities. They publicly reported achieving millions of QPS capability, millions of queries per second.
Millions.
Yeah, and significant cost savings by standardizing their API infrastructure on APISX. This demonstrates how a robust API gateway can not only manage immense traffic during critical events like product launches, but also drive tangible return on investment through operational efficiency.
Millions of queries per second for a smartphone launch. That's an incredible testament to their raw power.
Indeed. Another fascinating case is Tencent Timi Studio Group, one of the world's largest video game developers, known for games like Honor of Kings. They developed their own internal gateway called TAF6 based on Apache APISX, specifically tailored for their gaming needs. This addressed the incredibly demanding requirements of low latency, massive concurrent users in real-time gaming environments where every millisecond counts for player experience.
Yeah, lag is death in gaming.
It's exactly. It shows how API gateways are adapted for even the most specific and high-pressure use cases.
Gaming is definitely a unique, high-demand scenario. What about more traditional industries undergoing digital transformation? Are they using gateways too?
Oh, absolutely. A great example from a traditional sector is the leading Seaport Group. They utilized API 7 Enterprise, which is a commercial version of API-6, to enhance their invoicing processes and optimize intermodal transport coordinating ships, trucks, trains. This showcases how API gateways facilitate critical digital transformation even in established industries, streamlining complex logistics and improving efficiency across a vast network of partners and systems. Then there's DataVisor, a leading fraud detection company. They streamlined their operations using Apache APISX. They reported greater system stability and faster processing for their high-stakes security application, where detecting anomalies and preventing fraudulent transactions in real time is absolutely paramount. The gateway became a linchpin in their ability to handle massive data streams for fraud analysis quickly and reliably.
And even in the automotive world, which is undergoing massive shifts towards electric and connected vehicles, are they using them there?
Precisely. Lotus Cars, the iconic British sports car manufacturer, leveraged API 7 Enterprise for their modern automotive technology and connected car services. This illustrates the gateway's crucial role in the development of new energy vehicles and intelligent automotive solutions, enabling secure communication between vehicles, cloud platforms, and external services for features like over-the-air updates, remote diagnostics, infotainment, and more. These examples clearly demonstrate that API gateways are not just theoretical constructs. They're practical, impactful solutions yielding immense value and strategic advantage across diverse industries.
And that brings us to the tangible business impact and return on investment. What are the measurable benefits organizations are actually seeing by investing in API gateways? What's the bottom line?
The financial benefits are quite clear and compelling. Organizations have reported significant improvements, including things like a 21% increase in API ROI, meaning their investment in APIs yielded 21% more value, largely because API gateways reduce friction and consumption barriers for developers and partners, making APIs easier to use securely.
Makes them more valuable.
Exactly. There are also documented reports of up to a 30% reduction in development costs. This comes from standardized API management practices, reusable infrastructure components provided by the gateway, and streamlined development workflows, less reinventing the wheel. All of this, combined with enhanced agility, directly translates to a faster time to market for new products, services, and features, giving businesses a crucial competitive edge.
So it's not just about saving money on operations, but also about accelerating innovation and getting products out the door faster. making money faster.
Exactly. Operationally, it leads to truly significant efficiency gains. You see vastly improved system reliability because the gateway handles common failure modes like circuit breaking and provides intelligent load distribution. There's enhanced troubleshooting capability due to centralized monitoring and logging. Teams can quickly pinpoint issues across distributed systems much faster. This reduces manual processes and firefighting, freeing up engineering teams to focus on core innovation rather than just keeping the lights on. And critically, these improvements in reliability, performance, and accelerated feature delivery lead directly to better user experiences, increased customer satisfaction, and ultimately higher revenue, stronger brand loyalty, and improved customer retention. It's a complete and powerful circle of positive business impact.
We've painted a pretty compelling picture of API gateways so far, highlighting their immense value and the problems they solve. But in the world of technology, there are always choices and trade-offs. Nothing's perfect. What are the alternatives to API gateways? And if they're so great, what are their limitations and common challenges that organizations inevitably face? It's important to have a balanced, realistic view.
Absolutely. Critical point. While API gateways are incredibly powerful and often the ideal solution, they aren't the only solution for every single scenario. And like all technologies, they come with their own considerations. Let's look at some prominent alternatives first. One that frequently comes up in conversations around microservices is a service mesh architecture. You hear about things like Istio, Linkerd, or Console Connect.
How does a service mesh fundamentally differ from an API gateway? They both seem to manage traffic, right? It gets confusing.
That's a great question, and it's just a common point of confusion. A service mesh primarily excels at managing east-west traffic,
East-west.
meaning communication between services within a microservices environment, internal traffic. It provides highly granular control over internal service-to-service communication, offering features like robust traffic routing, load balancing, and strong zero-trust security at the application layer, deep inside your network. You'd typically prefer a service mesh if you need advanced observability, fine-grained policy enforcement, and a comprehensive security posture deep within your internal service-to-service communication. The trade-off, however, is significant operational complexity. It's like building an incredibly intricate, highly optimized internal highway system for our city, complete with its own traffic cops and monitoring at every single intersection. It can be overkill for simpler needs and doesn't directly address the external entry point issue.
Okay, so gateways are generally for the north-south traffic. The front door and service meshes are more for internal east-west traffic. What about the simplest approach, just direct communication, no middleman?
Indeed. Direct service communication is the most straightforward approach. Here, client applications or other services talk directly to back-end services, completely eliminating any intermediaries. This minimizes latency and infrastructure complexity, as there are no additional hops or components to manage. Sounds great, right?
Seems simpler.
It is, initially. This might be preferred for very simple, tightly coupled architectures with limited API requirements, or maybe in highly controlled internal networks where you trust every component implicitly. You sacrifice centralized policy enforcement, consistent security implementation, and unified monitoring. This becomes incredibly unwieldy and risky as your system grows in complexity. It's like having no central station or concierge and just letting everyone call individual businesses directly. It works for a very small village, but not a sprawling metropolis. It doesn't scale from a management perspective.
And what about serverless platforms that abstract away a lot of infrastructure? Things like AWS Lambda.
Serverless computing platforms like AWS Lambda, Azure Functions, or Google Cloud Functions are excellent for simple, event-driven API scenarios. They offer completely abstracted infrastructure management. You don't manage servers. Automatic scaling based on demand. A pay-per-use pricing model. Very cost-effective for bursty workloads.
Sounds appealing.
They're great for smaller, specific functions or micro APIs, hooking things together. However, they typically lack the sophisticated routing, the comprehensive security features like complex auth-z or WAF integration, and the advanced performance optimization capabilities like caching that are required for complex, high-traffic enterprise applications with diverse needs. They are more about executing individual functions in response to events, less about holistic API management for external consumers.
So a gateway isn't always the only right fit, but it usually comes with a lot of advantages for large, complex systems dealing with external traffic. Can you summarize those key advantages and then, critically, their inherent limitations? Let's get the pros and cons clear.
Okay, the advantages of API gateways are truly numerous and significant. They provide centralized control over all your API traffic, simplifying management and governance dramatically. They enable consistent policy enforcement across all your APIs, security, write limits, data transformations applied uniformly. They offer greatly enhanced security through centralized authentication, authorization, rate limiting, and comprehensive auditing, acting as a powerful defensive perimeter. They deliver significant performance optimization through features like caching, intelligent load balancing, and traffic shaping, making things faster and more reliable. And finally, they vastly improve observability with consolidated metrics, logging, and distributed tracing, giving you a clear picture of your API ecosystem's health. You know what's happening.
So, a lot of benefits for managing complexity and scale, security, performance. What are the inevitable downsides or limitations that organizations need to be aware of? The cons.
Right, the limitations. The primary ones include the potential for them to become a bottleneck if not properly scaled, configured, and managed. It's a central point, after all. They can represent a single point of failure if redundancy and high availability aren't meticulously built in from the start. You absolutely need multiple instances. There's also a slight but inherent latency overhead due to the additional network hop that every request must take through the gateway. It's physics. Though, as we've discussed, this can often be minimized to milliseconds and offset by caching.
An extra step.
Exactly. They can introduce complexity in configuration management, especially in very large-scale deployments with many APIs and intricate routing rules. Managing all those rules can get complicated. And finally, relying heavily on a specific vendor's proprietary API gateway solution can potentially lead to vendor lock-in, making it difficult or costly to switch providers down the line. Something to consider carefully.
Given these potential pitfalls, what are the most common challenges organizations run into when implementing and operating API gateways? How do these limitations actually manifest in the real world?
Organizations frequently face a few recurring challenges. Performance bottlenecks are common, often manifesting as latency spikes during peak hours or just general throughput limitations. This usually stems from improper configuration, maybe inefficient routing rules, maybe poorly tuned caching, or simply inadequate capacity planning for expected loads. Under provisioning.
Didn't buy enough server power.
Basically. Configuration complexity is another big one. Struggling with policy management, routing rule maintenance, versioning across multiple environments, dev, staging, prod. It can be a real headache, especially without robust automation and testing. Security vulnerabilities are a critical concern. These can rise from inadequate authentication mechanisms, insufficient rate limiting allowing brute force attacks, or, very commonly, misconfigured access controls that inadvertently expose sensitive data or internal functionality. Leads to breaches. Then there are monitoring and observability gaps, where teams have limited visibility into request flows, performance metrics, and errors. Makes it incredibly difficult to diagnose and troubleshoot issues in real time. You're flying blind again. And finally, scalability limitations can emerge if the initial architecture isn't designed for elasticity, leading to resource constraints or hitting connection limits as traffic grows unexpectedly. You didn't plan for success.
So given these common challenges and limitations, how do organizations effectively manage these risks and build resilient, future-proof API gateway deployments? What are the strategies for success? How do you avoid these traps?
Effective risk management strategies are absolutely crucial for success. It's not just about the tech, it's about the process. For security risks, it involves a multi-pronged approach. Comprehensive threat modeling early on to identify potential vulnerabilities before you build. Regular security assessments like vulnerability scanning and penetration testing by ethical hackers. And robust incident response planning so you know exactly what to do when, inevitably, something bad happens. It demands a defense in-depth strategy, layering security controls. For operational risk management, the focus is squarely on reliability, disaster recovery, and business continuity. This means designing for redundancy with active gateway clusters across different availability zones or regions, implementing robust backup and restore procedures for configurations, and proactive monitoring with automated alerting to detect issues before they impact users.
And given the many choices of vendors, how do you manage that specific risk of getting locked in or picking the wrong horse?
Absolutely. The vendor risk assessment is vital. It means thoroughly evaluating a vendor's stability, their product roadmaps, do they align with yours, the quality and responsiveness of their support, and critically, their exit strategies. What happens if you need to switch? How hard is it? You need to understand your dependency and have a plan B. For compliance risks, it's about implementing ongoing monitoring and audit capabilities to ensure continuous adherence to regulatory requirements like FIHIA or GDPR. This often involves automated checks and clear, immutable audit trails of all API access and configuration changes. And finally, there's technology evolution risk. The tech landscape changes fast. This involves planning for potential obsolescence of older gateway versions or underlying technologies, anticipating new vulnerabilities that emerge, and managing compatibility issues that naturally arise from rapid technological changes. It's about building for the present while constantly anticipating and preparing for the future. Keep things up to date.
Speaking of the future, let's turn our gaze to what's next. The technology landscape is always shifting, faster and faster, it seems. How are API gateways poised to evolve? What exciting trends are shaping their tomorrow, making them even more powerful and intelligent?
The future of API gateways is incredibly dynamic and promising. There are several transformative trends converging right now. One of the most significant and exciting is the increasing artificial intelligence integration.
AI in an API gateway. That sounds like something straight out of a sci-fi movie. How would that even work in practice? What would it do?
It's rapidly becoming reality, actually. AI and machine learning will enable truly intelligent gateways. We'll see AI-powered threat detection, where the gateway analyzes traffic patterns in real time to identify anomalies, potential attacks like sophisticated DDoS or API abuse or just unusual behavior, flagging and even automatically blocking security issues before they cause any impact. Imagine an AI that learns your normal traffic patterns for each API and immediately spots something fishy.
That's powerful. Proactive security.
Exactly. By 2025, we anticipate AI enabling automated policy generation. The gateway could suggest or even create security or rate-limiting policies based on observed usage patterns, simplifying management significantly. We'll also see dynamic routing optimization, allowing gateways to autonomously adjust traffic routing based on real-time network conditions, back-end service health, even predicted user demand, ensuring optimal performance automatically. And finally, predictive scaling, where AI allows gateways to autonomously adjust their own capacity scaling up or down based on anticipated load, ensuring seamless handling of traffic spikes without human intervention. This truly means smarter, more autonomous, and significantly more resilient gateways.
That would certainly reduce a lot of manual configuration and operational overhead. Let the machine handle the tuning. What about its interplay with edge computing? You mentioned that earlier as a deployment pattern.
That's another major transformative trend. Edge computing integration will lead to highly distributed API management solutions. This means deploying lightweight, intelligent API gateways much closer to the users or the data sources right at the edge of the network, rather than routing all traffic back to a central cloud data center first. This approach delivers ultra-low latency responses, crucial for real-time applications like autonomous vehicles, augmented reality experiences, or critical IoT sensor networks in factories where milliseconds matter. It also significantly optimizes bandwidth by processing data locally and only sending summarized or critical information back to the core. Less data flying around. Imagine the gateway intelligence right there at the source of data, not miles away in a data center.
And the combination of serverless, that function-based execution with that edge deployment must be powerful too.
Exactly. The trend of serverless edge computing combines the benefits of function as a service, like Lambda at Edge or Cloudflare workers, with edge deployment. This creates incredibly highly scalable and cost-effective API management solutions. You can run small pieces of code directly at the edge, triggered by API calls, with automated scaling and a true pay-per-use pricing model right where the data originates or the user connects. This is ideal for lightweight, bursty, and geographically distributed API workloads, personalization at the edge, for example.
So looking at these emerging technologies, what do the industry predictions say about the overall market trajectory? Still growing like crazy.
The market growth is projected to continue its explosive trajectory. We mentioned that $51.11 billion by 2033 figure for the overall API management market. Just massive. Beyond just growth, we'll see increasing technology convergence. The lines are definitely blurring between traditional API gateways, service meshes, content delivery networks, CDNs, and application delivery controllers, ADCs. This will likely lead to unified management platforms that offer a more holistic approach to traffic management, security, and performance across both external north-south and internal east-west API calls. One platform to rule them all, maybe.
That sounds like a consolidation of functionality, potentially simplifying the architectural landscape, which would be nice.
It could, yes. Furthermore, regulatory evolution will inevitably increase its focus on privacy, data sovereignty, where data lives, and compliance automation. This will drive innovation in areas like privacy-preserving technologies within the gateway and automated audit trails. And we'll see an acceleration of industry standardization efforts. Around API specifications like the Open API Initiative, formerly Swagger, security protocols like OAuth enhancements and interoperability standards, maybe through organizations like the CNCF, Cloud Native Computing Foundation. This ensures greater interoperability, making it easier for disparate systems and different vendors' tools to communicate securely and efficiently, fostering an even more connected digital ecosystem.
So what new technical capabilities will these future gateways be expected to handle as standard? What's coming down the pipe feature-wise?
The capabilities will expand significantly. GraphQL and async API support will become standard table stakes, no longer niche features. Async API specifically addresses event-driven architectures, which are becoming huge. This will enable even more flexible data access patterns and robust real-time communication, including sophisticated subscription management for live data feeds, like WebSockets or server-sent events. We'll also see widespread WebAssembly integration. WebAssembly, or WASM, is a high-performance binary instruction format.
WASM, right, it's popping up everywhere.
It is. This allows developers to integrate custom processing logic, protocol extensions, and performance optimizations directly within the gateway itself, written in languages like Rust or Go, and compiled to WASM, bringing unprecedented flexibility and speed for custom tasks right at the edge.
And looking even further into the future, with quantum computing looming on the horizon, that potentially breaks current encryption, right? How will gateways adapt to that potential threat?
That's a critical and fascinating area. Quantum-safe cryptography, QSC, or post-quantum cryptography, PQC, will become absolutely essential. To protect against the unprecedented cryptographic threats posed by future fault-tolerant quantum computers that could break algorithms like RSA and ECC, which underpin much of today's internet security.
Scary stuff.
It is. This will require gateways to support new post-quantum algorithms currently being standardized, like Crystal's Kyber, Crystal's dilithium, and likely hybrid security models combining classical and quantum-safe methods during the transition. Gateways need to handle this crypto agility. Also, a complete shift towards zero-trust architecture will transform security models, moving away from trusting things just because they are inside the network perimeter, toward continuous verification and context-aware access control for every single request, regardless of its origin. Never trust, always verify. The gateway will be the key enforcement point for this continuous verification, checking device posture, user identity, location, behavior, etc. for every API call.
So there's also a significant emphasis on future research to push these boundaries even further.
Indeed. Beyond these trends, future research areas include truly cutting-edge topics, like privacy-preserving technologies such as homomorphic encryption, which theoretically allows computation on encrypted data without decrypting it first. Imagine the privacy implications. Or distributed consensus mechanisms for globally distributed gateways, ensuring consistent state and policy enforcement across continents seamlessly. And even direct quantum computing integration, perhaps for specialized tasks beyond just crypto, revolutionizing security and performance in ways we can't fully predict yet. It's a field absolutely brimming with innovation and continuous evolution. It won't stand still.
This has been an incredibly insightful deep dive into the world of API gateways. Really fascinating stuff. Now, for you, our listener, if you're looking to implement or maybe optimize an API gateway within your own organization, what's your practical blueprint for success? What are the first steps and crucial priorities to get it right?
All right, bringing it back to action. A truly effective implementation starts with a solid foundation. You can't just buy a tool and plug it in. The very first step is a thorough initial assessment and planning phase. This means conducting a comprehensive API inventory. Do you even know all the APIs you have? Where they are? Who uses them? Analyze your current traffic patterns and volumes. What are your peaks? Where does traffic come from? And meticulously gathering stakeholder requirements. What do your business teams really need? What about developers? Security experts? Operations? Understand what you have, how it's used today, and what your ultimate business goals are for this infrastructure investment. Why are you doing this?
And after that initial deep dive into your own landscape, what comes next?
Once you have a clear picture, develop proof of concept, PC development. Don't try to boil the ocean. Start with a limited scope implementation of the API gateway. Pick a couple of non-critical APIs first. Use it to demonstrate the value, validate your architectural assumptions. Does this tool actually work in our environment? And crucially, help your team gain practical experience and familiarity with the chosen solution. Build confidence.
Learn by doing.
Exactly. Following that, create a robust technology evaluation framework. Use weighted criteria covering functional capabilities. Does it do what we need? Performance benchmarks. Is it fast enough? Security features. Is it secure enough? And operational aspects. Can we actually run this thing? Tailor it to your organization's specific needs. This structured approach will help you make an informed, objective choice on the right gateway solution, not just based on marketing hype. And finally, team preparation and training are absolutely crucial. Don't underestimate this. Invest in upskilling your teams in API management best practices, gateway configuration specifics, operational procedures, troubleshooting. This ensures smooth adoption and efficient ongoing management. And of course, conduct a thorough risk assessment and mitigation plan before you begin full implementation. Identify technical, operational, business security risks, have a clear contingency plans in place. What could go wrong and what will we do about it?
Once you're past the strategic planning stage and ready to actually build, what are the absolute prerequisites and requirements for setting the stage for a successful API gateway deployment? What needs to be in place?
You need to clearly define your infrastructure requirements. Sizing dedicated hardware or cloud instances appropriately for expected load and anticipated growth. Don't just size for today. Ensure you have enough compute, memory, and network capacity. Your network architecture needs to be meticulously designed to support optimal gateway placement, edge.internal, efficient traffic flows, and robust security boundaries. This includes precise load balancer configurations in front of the gateway cluster, DNS settings, firewall rules. Get your network team involved early.
Yeah, network is key.
Definitely. You also need a robust security infrastructure in place for the gateway to integrate with. Your identity systems like Active Directory, Okta, certificate management for TLS SSL, maybe secrets management systems, policy enforcement tools. Critical, too, is establishing a mature monitoring and observability strategy from day one. Deploy metrics collection systems like Prometheus, robust log aggregation like Splunk or ELK Stack, and distributed tracing systems like Jaeger or Zipkin that the gateway can feed into. This provides the vital visibility you need to ensure health and troubleshoot quickly. Don't add monitoring as an afterthought. And finally, robust development and operations integration is key. Think CI/CD pipeline integration for automated testing and deployments of gateway configurations. Using configuration management tools like Ansible, Terraform to prevent configuration drift. And having comprehensive deployment automation. Treat your gateway config like code.
And when you're actually implementing with limited resources and time, what should be the absolute top priorities? Where should organizations focus their energy first to ensure the greatest impact and minimize risk? What comes first?
Great question. Prioritization is everything. The security foundation must be the highest priority, no compromise here. Given the gateway's critical role as the single entry point and protector of sensitive data, implementing multi-layer security, authentication, WAF, rate limiting, adhering strictly to the principle of least privilege, and conducting regular security reviews and penetration tests is absolutely paramount. Get security right first.
Job number one.
Absolutely. Next, performance optimization requires early and continuous attention. Ensure adequate capacity, acceptable latency under load, and reliable operations. Don't wait until users complain about slowness. Monitor P99 latency from the start. After that, establish operational excellence early. Set up comprehensive monitoring, logging, alerting, and troubleshooting capabilities as you build. Proactive detection and rapid response are key to maintaining reliability and trust. Know how you'll operate it before it goes live. Then comes integration planning. Thoroughly address how the gateway will integrate with existing backend systems, your current development workflows, how do developers onboard new APIs, and operational processes, including that full CI/CD integration. Make it fit smoothly. Lastly, develop a strong governance framework. Define clear policies for API design, security standards, lifecycle management. Establish approval processes for new APIs or changes. Implement robust audit capabilities. This ensures consistency, compliance, and control as your API ecosystem inevitably grows organically over time.
What an incredible journey we've taken today, diving deep into the world of the API gateway. We've seen how this seemingly humble technical component has evolved into really a strategic imperative for digital transformation, enabling unprecedented scalability, ironclad security, and continuous innovation across every industry imaginable. It's the silent workhorse that powers so much of our interconnected digital lives.
And the market numbers don't lie, do they? The explosive growth projected for the API gateway and broader API management market dramatically underscores their strategic importance. From financial services handling real-time payments with stringent compliance needs, to media giants streaming content to millions of concurrent users, to manufacturers connecting complex IoT devices at the very edge of their operations, API gateways are truly the indispensable glue holding it all together.
It's truly fascinating to witness how a single, well-architected piece of infrastructure can have such a profound and far-reaching impact on digital business and ultimately user experience. From enabling millions of queries per second for smartphone manufacturers like Honor and streamlining fraud detection operations at DataVisor, to powering cutting-edge connected car services at Lotus, the real-world success stories are compelling proof of their value.
It really highlights that in our increasingly interconnected and API-driven world, that single point of entry isn't just a technical detail on an architecture diagram anymore. It's the intelligent nerve center of modern enterprises. It's where security policies are enforced consistently, where traffic is optimized for peak performance, where critical insights into system health are gathered, all while abstracting away the immense internal complexity.
And as we look to the future, with AI integration promising autonomous optimization and threat detection, quantum-safe cryptography protecting against tomorrow's most sophisticated threats, and edge computing bringing intelligence and ultra-low latency closer to the data source, the API gateway isn't just evolving, it's actively transforming into something even more intelligent, distributed, and absolutely crucial. It will undoubtedly continue to be a fundamental linchpin in the digital economy for years to come.
This truly raises an important question for you, our listener, to consider as we wrap up. Given this rapid and continuous evolution towards AI-driven, quantum-safe, and edge-native gateways, what existing digital infrastructure within your world, perhaps a legacy system, a core business process, even an older gateway, might be the next to undergo such a fundamental transformation? What's your next single point of entry that needs to be made resilient, intelligent, and future-proof to thrive in the accelerating digital age?
Food for thought indeed. Thank you so much for joining us on this deep dive. We hope you walk away well informed, perhaps a little more curious, and certainly with a greater appreciation for the unsung heroes of our digital world, like the API Gateway. Until next time, keep digging deeper.